linear independence. That will be the topic of this section. I will write that for now on as LD. Suppose we have the vector space V, which is R3. So we have the set, just the set V, R3. The question is, do these three vectors span R3? Do their vectors V1 equal to 1, 0, 1, V2 equals 2, 0, 1, and V3 equal 1, 2, 1. So 1. Do the vectors V1, V2, V3 span R3? That is, can any vector in R3 be written as a linear combination of the vectors 1, 2, and 3? The vectors. Okay, so we take an arbitrary vector in R3. Call it ABC. I'm going to have enough space, but let's put it there. And the question is can this vector be obtained by taking a multiple of vector 1 plus a multiple of vector 2 plus a scalar multiple of vector 3? Okay, that is, can I find C1, C2, and C3? Can I always find C1, C2, and C3? That is, will they be well defined? Okay, so what we have is the following. It's C1 times V1, which is 1, 0, 1, plus C2 times V2, which is 2, 0, 1, plus C3 times V3, this is V3, and we want to get ABC. We want to be able to get ABC. Okay. So let's see what the first component will look like. You're going to get 1C1 plus 2C2 plus 1C3, and this, of course, will equal A. You're also going to get, for the second component, 0 times C1 plus 0 times C2 plus 1 times, oops, didn't mean to do that one yet. I meant to come over here, plus C3 times 1. That is 1C3. And this is going to equal to B. Now for the third component, you're going to have 1 times C1 plus 1 times C2 plus, you guessed it, 1 times C3, and is going to equal to C. So what we have is a system of equations in C1, C2, and C3. Okay. Well, this gives us a matrix. The coefficients of C1, the coefficients of C2, the coefficients of C3, and ABC, the right side values. Now, the question is, could we have gotten here a bit more quickly? The answer is yes. If you look at the vector 1, whether it's written horizontally or vertically, I could have said 1, 0, 1. I could have written it that way. the bottom line is that is the first column. And the second vector 2, 0, 1, look at that. It is the second column. And vector 3, 1, 2, 1 should be the third column. And I need to find out why I put a 1 and not a 2 there. So let's look at that. That's right here. That should be a 2. And why is it not a 2? Did I not write the vector down right? I'm looking at vector 3. Oh yeah. The second component should have been 2C3. That should have been a 2. Absolutely. Okay. So it is working like a charm. 1, 2, 1, that is vector 3, is the third vector. You don't even have to put them in that order. As long as you write this as one column, and this as another column, and this as yet another column, you'll be okay. The order doesn't really matter. Okay, so now we need to solve this last matrix. And now, everything I'm going to erase right here, I'm going to erase more, but everything that I just erased, you don't need to do anymore. You can just go from the set of the 3 vectors right to there. You can go right there. Okay. But since I need this room, I'm going to erase everything but the matrix. Okay. So once I erase my physical board, we are going to solve this matrix, this augmented matrix. I haven't used that word in a while. It's augmented because there's a line in the matrix. Somewhere inside the opening and closing bracket of the matrix, there is a vertical line, hence augmented matrix. Okay, so to save a little space, I'll say to clean up column 1, that's my first non-zero entry in row 1, I want to get that entry in the bottom to be a 0. So I'll do row 1 minus row 3. So row 1 does not change. Row 2 does not change. Row 3 becomes 0, 1, 0, and A minus C. I am going to interchange those 2 rows. So I get 1, 2, 1A, 0, 1, 0, A minus C, and 0, 0, 2, and B. Second row, there's my leading entry. I want to get the 2 above to be a 0. So I'll do row 1 minus 2 row 2s. This here is row 1, and 2 row 2s is 0, 2, 0, 2 A's minus 2 C's. And if I subtract, I get 1, 0, 1. A take away 2A is negative A, and we have to take away negative 2C, that is we add 2C. Because I hate losing minus signs, I'm going to write 2C minus A. Kind of easy to lose that sign. So the first row becomes 1, 0, 1, 2C take away A. The second row is just the second row. And the third row for now is okay. In fact, I hate getting fractions, but let's divide by 2 now. I get 1 and b over 2. Okay. So now I'll just do row 1 minus row 3, and that should be it. 1 minus 0 is 1. 0 minus 0 is 0. 1 minus 1 is 0. And you're going to get 2c minus a minus b over 2. The second row is this. And the third row is simply this. And you have to be careful. You can't say, oh, yeah, I got the identity, everything's fine. That's not necessarily true. We'll talk about that in a moment. What I mean by fine is we figured out what A, B, and C are. It's not enough just to say what A, B, and C are. They have to always be well defined. That's the C. So we found from the first row that C1 is 2C minus A minus B over 2. And C sub 2 is going to be A take away C. And C sub 3 is just going to be B over 2. Now, if you got that C1 is A plus B over C, and C2, I don't really care what you got, and C3, I don't care what you got. C1 is not always well defined. You can have any A, B, C, because C can't be 0. C can't be 0. You had A plus B over C minus 2. Well, then C can't be 2. That is, you can't get any old vector in R3. The second component can't be 2. Sorry, the third component. You can only get A, B, and then not 0. You can get any for the first so far, any for the second, but you can't get 0 or 2. You can't get 0 and you can't get 2. And if C3 was A minus 2C over B squared, then B, you can't have 0. You can't just get any old A, B, C. If you had this. But no matter what A, B, and C are, you can double C. You can take away A from that. And then you can compute half for B and subtract it. Subtract it from 2C minus A. No matter what A and C are, you can subtract it. No matter what B is, you can divide it by 2. Okay, so here it is. We were able to find C1, C2, and C3. And most importantly, or just as importantly, it is always well defined. It is always well defined. It is absolutely well defined. So what we can say is, yes, the span of vector 1, vector 2, vector 3 does equal to R3. We know it contains R3, but think about it. Is it going to contain more? Can it possibly contain more? If you're going to have a set that contains triples, are real numbers. Everything, each of these are real numbers. You'll never get anything larger than R3. Now, I want to show you that this really, really works. Here is what one can call your recipe. So let me try to sneak R3 here. Now, what if I told you that A is 3, B is 4, and C is -1? Well, then C1 will be 2 times C, which is -2, minus A, which is 3, minus half of B, which is 2. So it looks to me like we get -7. And C2 would be A minus C. It would be 3 minus a -1, which is 4. And C3 is just half of B. It's B over 2. 4 over 2 is 2. Now, I claim that those are the coefficients that will get me the vector 3, 4, -1. But let's see if I'm out of my mind or not. It will work unless the concept will work. If it doesn't work, it's because I made a silly error in reducing. But if I didn't make an error, then everything's going to work out fine. Remember, C1 V1 plus C2 V2 should give me any A, B, C. So I pick the A, B, and C, and that gives me the values for C1, C2, and C3. So what we want to know is the following. Is C1 V1 plus C2 V2 plus C3 V3, does it equal to A, B, C? Where A is 3, and B is 4, and C is -1. And C1 is -7. And V1 was 1, 0, 1. Plus C2 is 4. Times V2, which remember was 2, 0, 1. And C3 is 2, so it's plus 2 times V3, which was 1, 2, 1. And the question is, does this give me 3, 4, -1? Well, let's look at the first component. Let's see if we get 3. We have -7 plus 8, that's 1, plus 2 more is 3. So here I got this 3. Is the second component going to be 4? Well, -7 times 0 is 0. And 4 times 0 is 0. You add up the 2 zeros, you get 0. But now you add 4. And 0 plus 4 is 4. Let's look at the last component. -7 times 1 is -7. 4 times 1 is 4. That's -3. Plus 1. Plus 2. -3 plus 2 is -1. So yeah, I found it. This here down here is the recipe. I solve for C1, C2, and C3. And you plug in any A, B, and C, and you'll get C1, C2, C3. Again, if C3, for example, was B over 2C, I couldn't allow my C to be 0. Because then what would I put in for C3? What would C3 be? Something over 0. B is 4, so it'll be 4 over 2 times 0, which C was 0. 4 over 0 is not a number. So it wouldn't work. But here it did work. No matter what A, B, and C are, I can say what C1, C2, and C3 are. So work like a charm. Work quite well. You want to find out if a set of vectors span a set of vectors, a vector space. If it spans a vector space, then you take a linear combination of the vectors and you set it equal to an arbitrary vector in the vector space. You take a linear combination of the vectors that you want to know if it spans the vector space, and you set that equal to, you set the linear combination equal to an arbitrary vector in the vector space. Suppose we have the set S, which contains these four matrices. Sorry, these three matrices are there. Yeah. These three matrices. And the question is, does S span the set of all symmetric 2x2 matrices? Symmetric 2x2 matrices. Now remember, a matrix is symmetric if it equals its own transpose. So if you have X, Y, Z, and W, and it's supposed to equal its own transpose. That is, this first row is now the first column, this second row is now the second column. Well, surely X equals X, and W equals W. But Y is going to have to equal Z. And it even says it again. Y is going to have to equal Z. That is, symmetric equations are, 2x2 symmetric matrices are in this form. Let me write it down more clearly. It's in this form, where these entries are the same. So X, Y, and Z are any real numbers, but that non-main diagonal has to be the same. So that's what we want to know. Do the given matrices in set S, can they give us each and every matrix that is symmetric, 2x2? That is what we want to know. Okay, so I want to know if C1 times the first given matrix plus C2 times this matrix plus C3 times the third matrix, is it going to give me an arbitrary 2x2 symmetric matrix? A, B, B, and C. Do I get that? Can I figure out what C1, C2, and C3 need to be so I do get it? Well, let's look at the 1, 1 position for the left side. You're going to have C1 times 1, which is C1. And you're going to add 0 and then another 0. It's just C1. And then you're going to have C1 times 0, which is 0. C2 times 1, which is C2. And then another 0. 0 plus C1 plus 0. 0 plus C1 plus 0. Oops, this is C2. 0 plus C2 plus 0 is C2. C1 times 0 is 0. C2 times 0 is 0. C3 times 1 is C1. C3. 0 plus 0 plus C1 is, I'm looking at 1, but it's C3. Try it a third time. 0 plus 0 plus C3 is C3. And then you get C1 plus 0 plus 0, which is C1. Now, there's only one way this is going to be A, B, C, and, A, B, B, C. There's only one way that's going to happen. That implies that C1 must be A, C1 must be A, C2 must be B, C3 must be B, and C1 must be C. C1 must be C. Well, this tells me that A and C have to be the same. Okay, A and C have to be the same. Well, that's the problem. They don't have to be the same. That's the problem. They don't have to be the same. That is to be in the set of symmetric 2 by 2 matrices, these do not have to be the same. There's no problem that the constant or scalar C2 and C3 have to be the same. The thing is, are there any constraints on A, B, and C? The answer is yes. A and C have to be the same. So once you find out that these have to be the same, so the only way a linear combination of the 3 given matrices in set S will give us a symmetric matrix is when B and C are the same. Sorry, A and C are the same. So it's not any old 2 by 2 symmetric matrix. You know, we can't get 1, 3, 3, 4. Why? From these 3 matrices. Why? Because for those 3 matrices to get symmetric, those 2 entries that I just boxed have to be the same. So the answer is no. S doesn't span symmetric 2 by 2 M-for matrices. No, S does not span symmetric 2 by 2 matrices. Okay. Again, how do you tell if a set of vectors span a space, a vector space? You take a linear combination, an arbitrary linear combination of those vectors, and then you set it equal to an arbitrary vector in the vector space. And if you can figure out what those arbitrary scalars need to be, and they're always, always well defined, you're okay. Sometimes they won't be. Suppose the vector space now is P2, the set of all vectors of degree 2 or less, including the zero polynomial. I meant to say V is a set of polynomials of degree less than or equal to 2. Suppose S has 2 vectors, or 2 polynomials. P1 of T, which I don't know, I'll call T squared minus 2T plus 1, and P2, which is just T squared minus 1. So S has 2 vectors or 2 polynomials. The question is, does S span P2? Using those 2 vectors, can I come up with every polynomial in P2? So the solution is I do C1 times the first polynomial plus another scalar, call it P2, times the second polynomial. The question is, do I get an arbitrary polynomial in P2, which is a number times t squared plus another number times t plus a constant. Can I find C1 and C2? Well, P1 is t squared minus 2t plus 1 plus C2 times P2 of t, which is t squared minus 1. And we want it to equal to this. Let's collect like terms. Let's find out how many t squares we have. We have C1 t squares, and we're adding C2 t squares more. So we're going to have a total of C1 plus C2 t2 plus, how many t's we have? Well, we have negative 2c1 and none in the second one. How many constants do we have? Well, we have c1 plus negative c2, c1 minus c2. That's the constant. And this is supposed to equal to at squared plus bt plus c. Well, for this equal sign here to be valid, the coefficient of the t squares have to be equal. So c1 plus c2 must equal a. Notice they both have plus a number of t's. The number of t's on the left, negative 2c1, must equal to b. And the constant on the left, plus c1 minus c2, must equal the constant on the right. Now, if I can solve this for c1 and c2, and it's always well defined, c1 and c2 are always well defined. For any a, b, and c, we're okay. And if we get a contradiction, then we have a problem. Okay, so this, well, all right, why don't we set up our matrix? 1, 1, a. The second one is negative 2c1s plus no c2s, and it equals b. The third one is 1c1 minus 1c2 is equal to c. So this here is the matrix. Let's clean up the first column. Let's get rid of the negative 2 and the 1 by using row 1. I'll do 2 row 1s plus row 2. And I'll just do row 1 minus row 3. 2 of these are 2. And when I add negative, well, row 1 isn't changing. Sorry. I didn't put anything here. 2 of these, when I add that, gives me 0. 2 of these are 2. And when I add that, I still get 2. 2 of these are 2a's. And when I add the b to it, I get b. In the third row, row 1 minus row 3. 1 minus 1 is 0. 1 minus negative 1 is 2. And the last column, a minus c is a minus c. Now hopefully you see a problem already. These two left sides are the same. So they have to equal to the same thing. They have to equal the same thing. They can equal different things. Remember, a row in a matrix in an augmented matrix corresponds to an equation. The second row pretty much says that 2c2 is equal to 2a plus b. And the third row says 2C2 is equal to A minus C. So 2A plus B must equal to A minus C. Bringing everything to the left side, that is taking away A and adding C to both sides, gives us 0 on the right side. 2A minus A is A, plus B plus C. The only way we can find a linear combination, or the only types of linear combinations we're going to be able to get, is when A, B, and C, the sum of A, B, and C equal 1. The sum of A, B, and C must equal to 1. Now, that sounds amazing to me. And if I said it equals to 1, I didn't mean that. The sum of A, B, and C should add up to 0. A plus B plus C should add up to 0. And I'll show you that's the only thing that we can get when we take linear combinations of P1 and P2. Okay. These kind of got erased a little bit. So let me put it back. Okay. So I'm just picking any old numbers for C1 and C2. I'll let C2 be 2. Well, this gives me 6t squared. Sorry, 3t squared. 3t squared minus 6t plus 3. And I am going to add 2t squared minus 2. And when I add the like terms like 3t squared plus t squared, I get 5t squared. And this is the only t term. I have minus 6t, and positive 3 plus negative 2 is positive 1. You're not going to believe this. So when I add the A, the B, and the C, I can add them in any order. 5 plus 1 is 6. Minus 6 is 0. Or if you insist, 5 plus a negative 6 is negative 1, plus 1 more is 0. The only thing I can get any polynomial in P2 or below. But the A, the B, and the C, when you add them up, they have to be 0. So I don't know if I already wrote the answer, but no, this does not span. I suspect I didn't. Once I got this here, I should say no. S does not span P2. It does not. Why? Because I was only able to get polynomials of degree 2 or less, where the coefficients add up to 0. Once you get a constraint on A, B, and C, like A must equal C, or A plus B plus C must equal 0, or A equals B plus C, and whatever B and C add up to, that's what A has to be. No, it won't be in the span. That set does not span the space. If you have constraints on your coefficient, not on the coefficients, but you have constraints on what you were able to multiply. You had constraints on, in this last column, you had constraints on A, B, and C. You couldn't have any old arbitrary polynomial of in P2. Those two vectors, P1 of t and P2 of t, the linear combinations of P1 and P2 did not give you any old polynomial, any generic, any Can't think of the word. Arbitrary polynomial in P2. This is an arbitrary polynomial in P2. You may say, but P2 doesn't have to be degree 2. Fair enough. But nobody said that A couldn't be 0. It is a constraint on the span. A and B and C couldn't be any old numbers. They can be 4 and 2, that adds up to 6. And then the constant had to be negative 6. It's not any old one. They can't span that. This is not in the span. This is not an element of the span of P1 and P2 of T. It's not. Okay. Now we talked about null spaces before. The null space for AX equals 0. The set of solutions is the set of all vectors X such that AX equals 0. A times X equals 0, and that X is in the null space. If A times some specific vector equals 0, then that vector is in the null space. Okay, so consider AX is equal to 0, where A is, say, this matrix. 1, 0, 1, 1, 1, 2, 0, 1, 1. The question is, find the null space of A. Find the null space of A. Okay, so we want to reduce A. Remember, we want to solve this system of equations, or this augmented matrix. We put the 0 vector at the end. That's what it equals. It equals the 0 vector. Okay, now if we reduce this matrix by doing row 2 minus row 1, row 3 minus row 1, we get 1, 1, 0, 0, 0, 11, 0, 1, 0, 1, 0, 0. Okay? And now we'll do row 1 minus row 2, 1 minus 1 is 0, and we'll do row 2 minus row 3, plus 1 minus 1 is 0. And what that gives me is 1, 0, 0, 0. The second row we're not touching. The third row will be 0, 0, 1, 0. Then I just do row 2 minus row 3, and I get the identity matrix. So, if X were X1, X2, X3, this implies X is, well, X1 is 0, X2 is 0, and X3 is 0. So, the null space of A is simply the 0 vector. Let's try another one. So now, what is the span of the null space? The span of the null space of A, well, that is the null space. Linear combination of those vectors, in this case, since there's only one vector, the scalar multiple of this one vector is that vector. It's not usual that the only time the null space of A and the span of the null space of A will be equal is if the null space of A just has the zero vector. Remember, the null space of a matrix A is never empty because of a homogeneous system in AX equals 0, a homogeneous system of equations. The null space will never ever be empty because the zero vector is always the solution. A times 0 is always 0. And whenever we talk about the null space of A, we mean the solutions to AX equals 0. We always mean that. Null means 0. Okay. Consider AX equals 0. Consider the homogeneous system AX equals 0. 0 and X are there. And we want to find the null space of A. Find the null space of A, which equals to 1, 1, 0. 0, 1, 1 sounds good, and, well, how about this one? I want this 0, 1. I just want this to work out in a special way. How about 0, 1, 0, 1, and then 1, 2, 0, 1, and 1, 0, 0, negative 1. Suppose that's A. We want to find the null space of A. So we reduce A. We get 1, 1, 0, 0, 0, 1, 0, 1, 1, 2, 0, 1, 1, 0, 0, negative 1. And remember, augmenting it with the zeros. Everything we do, the things that we do to rows is we can multiply a row by a number. But when you multiply those zeros by a number, they stay 0. Other times, we add a multiple of this row to a multiple of that row. Well, multiples of zeros are zeros. And when you add those zeros, you still get the number 0. So, those right-hand numbers will never, ever, ever deviate from 0. If you want to keep writing them down, that's fine, but you don't need to. How about we do to kill off these numbers, row 3 minus row 1, and row 1 minus row 4. And what that's going to give us is 1, 1, 0, 0, 0, 0, 1, 0, 1, 0, and row 3 minus row 1. This minus that is 0. This minus that is 1. 0 minus 0 is 0. 1 minus 0 is 0. And then row 1 minus row 4. 1 minus 1. 1 minus 0. 0 minus 0. 0 minus negative 1 is 1. So we get that matrix. Make sure I didn't make a silly mistake. Okay. I'm going to use this row to kill off these ones. I'm going to do row 1 minus row 2. I'm going to do row 2 minus row 3. And row 4 minus row 2. Row 1 minus row 2 will give me 1, 0, 0, negative 1. Row 2 is not changing. Row 3, row 2 minus row 3 will give me triple 0 and then a 1. And row 4 minus row 2, since they're exactly the same, I'm going to get all zeros. And this matrix is in reduced row echelon form. This is a leading one, and this is a leading one. So column 1 has a leading 1, column 2 has a leading 1, column 3 does not, and column 4 does not. We'll call the columns x1, x2, x3, and x4. So x3 is arbitrary, call it R, and x4 is some other arbitrary number. So the question is, what's x2 and x1? Well, this one tells me that x1 minus x4, but x4 is s, is 0. That is, x1 is s. And the second row tells me that x2 plus x4 is 0. That x4 is s. So x2 plus s is 0. That means x2 is negative s. Okay. This is the same as no r's plus 1s, 0 r's minus 1s, 1 r plus no s's, and s is equal to no r's plus 1s. That is big X. X1, X2, X3, X4 is, you can think of as 0R, 0R, 1R, 0R, plus now the S's. 1S, negative 1S, 0 S's, and 1S. 0 S's and 1S. So, one more step. In each of those column vectors, I can factor out the common value. In the first vector, it's R. The second vector, it is S. So it's R times 0, 0, 1, 0. 0, 0, 1, 0. In the second matrix, I can factor out S. I get 1, negative 1, 0, 1. 1, negative 1, 0, 1. So this here is the null space. That's the null space. The null space of A is equal to R times 0, 0, 1, 0 plus S times 1, negative 1, 0, 1. Vectors in that form are in the null space. Now, what is the span of the null space? Remember, whatever vectors I put in the span of a set, the span is a linear combination of those vectors. Whatever vectors I put in the set, I have a set of vectors, and then I want the span of that set. It's the set of all linear combinations. span of the null space of A is, well, the span is always the same. And again, whatever vectors I put in here, I put in vectors v1 and v2. The span is going to be the set of linear combinations. The set of linear combinations of the vectors in there. Well, I want to get this. I want to get that. What vectors span the null space? The answer is those two vectors without the R and the S. If you take the span of those vectors, you'll get all those vectors. In this box here, there are many, many vectors because R and S can be anything. You really should say that x3 equals R where R is any number. x4 is equal to S where S is any real number. Okay. These two vectors, let me close the bracket a little bit sooner. These are the vectors that span the null space of A. Find the null space of A and cross off R and S's if there are any, and then say that's the set that spans the null space. Okay, moving right along. I'm going to talk about linear independence and linear dependence. Our set of vectors are either linearly independent or linearly dependent. Never both. So let S be the set of vectors v1, v2, all the way up to vn. Be a subset of vectors in the vector space. Let's take this nice and slow. We have our set of vectors in V, also called a subset of vectors in the vector space. This set S. This set S is said to be linearly dependent. Linearly dependent. If and only if there exists scalars C1 to Cn such that a linear combination of those vectors, those n vectors, linear combination of n vectors is going to have n scalars such that C1 V1 plus C2 V2 all the way up to Cn Vn is equal to the zero vector. Where not all CI's equal 0. One of those CI's is not 0. Okay, if you can find a linear combination of a set of vectors that is a number times the first vector plus a number times the second vector all the way up to a number times the last vector, and it equals 0, and some of their scalars were not 0, you have a dependent set. Example. Suppose x sub I, suppose c sub I is not 0. Okay? So C1, V1, all the way up to Ci, Vi, all the way up to Cn, Vn is equal to 0. Well, let's solve for Vi. First, let's solve for Ci, Vi. So Ci, Vi is equal to, we'll bring everything over. Negative C1, V1, minus C2, V2, all minuses, including the term right before, minus Ci minus 1 Vi, minus 1, minus the term right after, minus Ci plus 1, times Vi plus 1, all the way down to minus Cn, Vn. And now, since Ci is not 0, I'm going to divide each one by each term by Ci. Divide each term by Ci. Okay, linearly dependent means one vector is a linear combination of the others. One vector is a linear combination of the others. It depends. How do you get Vi? Oh, it depends on these other vectors. If you tell me what the other vectors are, I can tell you what Vi is. Because Vi is this. Vi is that. Let's look at a more concrete example. Real numbers. If S is equal to the set of vectors 1, 0, 2, 3, and 0, 1. These vectors are not independent. Excuse me. This is a set of dependent vectors because I can find non-zero scalars. Oops. Say 0, write 0. I want this to be the 0 vector. Now, of course, if I let C1, C2, and C3 be 0, I'll get the 0 vector. Because 0 times that vector is a 0 vector, 0 times that vector is a 0 vector, 0 times that vector is a 0 vector. You add up those 3 0 vectors, yes, you get the 0 vector. But that's not what we want. We want to find out if they don't have to be 0. Well, if you look at this, if you consider negative 2 times 1, 0, plus 1 times 2, 3, minus, minus 3 times 0, 1, minus 3 times 0, 1. Well, let's see what you'll get. For the first position, you have negative 2 plus 2, which is 0, minus 0 is still 0. For the second position, you get 0 plus 3 minus 3. Here. You do get 0, 0. And one vector can be expressed in terms of the others. Let's look at 2, 3. 1 times 2, 3 is just 2, 3. I'm going to bring every We'll bring the other two terms to the other side. When you bring this term to the other side of the equal sign, it becomes 2 times 1 is 0. You bring this to the other side, it becomes plus 3 times 0, 1. If you can write one vector in terms of the other vectors, you can take any vector in this set. Sometimes you can write, sometimes you won't be able to write this one in terms of the other two, or maybe you won't be able to write this one in terms of the other two, but maybe you can just write this one vector in terms of the other two. That's enough. That's enough. Okay, that's enough. This is a dependent set. This is a dependent set. It's also the same as these coefficients here in this equation, C1, C2, and C3. They don't have to all be 0. Some of them could have been 0. I mean, all I had to do was add, let me just erase this, please. All I would have to have done is added one more vector in the top set. I'll add one more vector in the top set, the vector 7, 4. Where did I get it? I just arbitrarily chose it. I will let C4 be 0. Because I know what I have in this line already is 0, 0. So if I add 0 times 7, 4, it didn't change the answer. It's 0, 0. If you can find a linear combination where of these 4 vectors, 1, 2, either 3 vectors or 4 vectors, if you can find the scalars where not all of them have to be 0, so yet you get 0, 0, that set is dependent. If, on the other hand, the only way you can get 0, 0, the only way is when all the coefficients, all the scalars are 0, then you have a linearly independent set. Okay, so why don't we state that above this line? I'll just make a couple of modifications and it'll be okay. It's linearly independent if and only if C1, C2 up to Cn equals 0, if and only if C1 equals C2 equals Cn is 0. Only if all the coefficients are 0. Oops, I guess I had the eraser in my hand when I did that. The set S is said to be linearly independent if C1, C1 plus C2, V2 equals 0 implies all those coefficients are 0. It's the only way this equation can be valid is only if all the coefficients are 0, you have a linearly independent set. Is the following set linearly independent? Is the set S equal to the set of vectors 1, 0, 0, 1, and say negative 2, 1, 1, 0. Is S linearly independent? So we take a linear combination and we set it equal to 0. Plus C2 negative 2, 1, 1, 0. We set it equal to the 0 vector. All the vectors here are in R4, so we get the 0 vector in R4. Well, this says negative C1 plus negative 2C2, or just minus C2, is equal to 0. The second line tells me 0C1, which I won't write, plus 1C2, which is just C2, equals 0. C2 is 0. And here we have 0C1, which is 0, plus 1C2, which is C2, equals 0. Well, I already have that one. The third row tells me that, so let me write down the third row answer. The fourth row I meant to say is 1C1, which is C1, plus 0C2 is 0, is equal to 0. So yes, I do have that C1 and C2 equals 0, but do the other equations contradict that? Well, the third equation certainly doesn't. It just says C2 is 0. Well, if C1 is 0, and then this is 0, and if C2 is 0, 2 times 0 is 0, and 0 minus 0 certainly is 0. So what we concluded was the only way this linear combination of the two vectors in S to give us the 0 vector is if those scalars are equal to 0. Therefore, C1 equals C2 is 0. Hence, S is a linearly independent set. So the answer to this question is yes. Yes, S is a linearly independent set. Notice that all of these tests for independent are for lead to homogeneous equations, because they're always going to equal to 0. You're always going to set the linear combination equal to the 0 vector. Now, unless otherwise stated, when I added these vectors, because this is a vector and this is a vector, unless otherwise stated, it's regular addition. You can just assume it's regular addition. Suppose V1 is 2, 1, 0, 1. That one can be arbitrary. The next one, I want it to be that. The third one is a bit more complicated. Well, I want it to be this. I want it to be that. The question is, like always, is S equal to the set V1, V2, V3 linearly independent in R4. Sorry, R3. No, it is R4. Because each vector has 4 values. When I just counted, I only saw 3 in R4. So, is a linear combination, set a linear combination equal to 0? An arbitrary linear combination. C1 times the first vector plus C2 times the second vector plus C3 times the third vector. Does this give me the 0 vector? Okay, now this is going to lead to a system of equations. For example, we have 2C1 plus 2C2 plus 3C3 is equal to 0. The second equation, second component, we get 1C1 plus 1C2 plus 1C3. And this is equal to 0. For the third component, we get 0C1 plus 1C2 plus 1C3 equals 0. And the last component is 1C1 plus 0C2 plus 1C3. This equals 0. Now, I can't talk to you, but for me, writing this down was painful. It was very painful. Let's just do one more step with this. Let's write it down as a matrix. So first, we write down those numbers. 2, 1, 0, 1. Then we write down those numbers. 2, 1, 1, 0. Then we write down the set of numbers, always including the signs. And it's augmented with the zeros. Now, could we have gotten to this matrix a bit sooner? The answer is yes, absolutely. This was the first vector, 2, 1, 0, 1. This here was the second vector, and this here was the third vector. You can get here more quickly. You can just go from the question right to this matrix. There's no level of difficulty there. All I did was write down V1 as a column, V2 as another column vector, and then V3 as the third column vector, as the third column. So what we need to do is just reduce this and see what the answers are. See what type of answer we get. So whether you do a lot of these a long way and then finally you start seeing here it works, or you just memorize, which isn't the greatest idea, but if you just memorize, you write them down as columns, it's okay. So let me write down this matrix, 2, 2, 3, 1, 11, etc., and we will reduce it. If you want to keep carrying along the zeros, fine. Not a big deal. How about we do row 1 minus 2 row 2s to kill this off. And do row 1 minus 2 row 4s. So row 1 is not changing. Row 1 minus 2 row 2s. 2 minus 2, 2 minus 2, 3 minus 2, and 0 minus 0. Third row, no change. Last row, row 1 minus 2 row 4s. 1 minus, sorry, this number 2 minus 2 of those. 2 minus 2 is 0. 2 minus 0 is still 2. 3 minus 0, or 2 zeros, is still 3. And the zeros won't change. Okay. Deal with this row. Let's get what's above it and below it to be 0. How about row 1, which has a 2 there? I will take away 2 rows 3's, which will put a 2 there. And same thing for the bottom. Row 4 has a 2 there. I'll take away 2 rows 3's. And this gives me 2, 0, 1, and 0. Row 2 is not being changed. Row 3 is not being changed. Row 4 is. 0, 0, 1. And of course I have 0 on the end. Okay. That second row is going to be history. Okay. It's going to be a row of zeros. Why? Because I'm going to take it away from row 4. Now, if you think about it, row 4 has a 1 here. That means, and everything else zeros. That is, it doesn't affect, adding multiples of this row to the other rows will not affect anything but the third position. Like if there was even a 4 here, just take away 4 of these, and that entry will be the only one that changes. It'll change to 0. If this number here was 14, just take away 14 of the last rows. Well, 0 minus any number of zeros is 0. 0 minus 14 zeros is 0. 0 minus 14 zeros is 0. And these were 14. 14 of those are 14. You take it away, you get 0. That is, all of these are just going to become zeros. 0, 1, 0, 0. And then this. The next thing I will do is divide the first row by 2. And I get that. And just put that row in the bottom. That is, this becomes the second row. That becomes the third row. Okay. C1, C2, C3. C1 is 0. C2 is 0. C3 is 0. And this doesn't contradict that. Okay. So, yes. S, just looking for the name of the set, we called it S. S is a linearly independent set of vectors in R form. But just S is a linearly independent set is enough. The coefficients, the scalars, had to all be 0. Now, if they are 0, not have to be 0, if you put in the zeros for the scalars, that linear equation, a linear combination will always work. 0 times v1 plus 0 times v2 plus 0 times v3 will equal to the 0 vector. always. But that doesn't make the set independent or dependent. It's when not could this coefficients be 0, but must they be 0. If they must all be 0, it's independent set. If they don't have to be all zeros, then you have a linearly dependent set. The big difference between having to use the coefficients that are 0 versus just using the zeros coefficients. Let's look at this one. Suppose V1 is 1, 2, negative 1. V sub 2 is 1, negative 2, 1. V sub 3 is negative 3, 2, negative 1. And V sub 4 is 2, 0, 0. And I actually worked out this column because I wanted to get a particular answer. So the question is S, which equals to V1, V2, V3, V4, linearly independent or linearly dependent? Is it a linearly independent set? Well, we wanted to figure this out. You write the first vector this way. The second vector becomes the second column. The third vector becomes the third column. Fourth vector, the fourth column. We'll augment it with the 0 vector. Now I worked this one out, and minus some silly error, I got it to be this: 1, 0, 0, 0, 1, 0, negative 1, negative 2, 0, and 1, 1, 0, and unquestionably correct all zeros. This is what I got. And the coefficients were C1, C2, C3. That is, I just wanted to see if this linear combination equaling to the 0 vector, does it imply that C1 must equal C2 must equal C4 equals 0? All the coefficients have to be 0. All of these have to be 0. Okay. Well, the reason I wrote that on the bottom is to motivate that columns are C1 through C4. The first row has a leading coefficient, so does the second, and that's the only one. That is, column 1 and column 2 have a leading coefficient. Columns 3 and column 4 does not. That is, C3 and C4 are said to be 3 variables. C3 can equal R. R is an real number. C4 is equal to S. S is an real number. On an exam, don't dare put just 3 dots like I did. Okay, now what is C1? This first row says 1C1 minus C3 plus C4 is 0. Well, bringing these to the other side, C1 is C3 minus C4. But C3 is R minus C4 is S. So C1 is R minus S. Now what is C2 equal? The second row tells me 1C2 minus 2C3s plus C4 is 0. So C2 is equal. Bringing this to the other side, it becomes 2C3. This C3 is R. So it becomes 2R. This goes over as minus C4. But C4 is S. So we get 2r minus s. That is what the c's can equal. We actually came up with an infinite number of solutions. We have an infinite number of solutions. An infinite number. One solution for each value of r and s that you can pick. And you can pick an infinitely many r's and s's. You can let s be 0, and r be 1, and then 2, and then 3, and then 4. Do that forever. And after you do that forever, you can let, I don't remember if I said s was 0. We'll say s is 0. Now s can be 1. R can now be 0 or 1 or 2 or 3 forever. And then s can be 2. And r can be 1 or 2 or 3 forever. And you can do that forever. And you can even touch a half and a third and a quarter. And r being the square root of 7. And s equaling pi to the second power. There are infinitely many solutions. So yeah. It doesn't imply. So this implies that the CI's are not all zeros, which implies that S is a linearly dependent set of vectors in R3. So that's the answer. S is not linearly independent. Now, your teacher's being picky if he or she says you better say S is linearly independent or not linearly independent. Because they're asking, is S linearly independent? And I really didn't answer it. I didn't say if S is linearly independent or S is not linearly independent. But linearly dependent means it's not independent. If it's independent, it's not dependent. If it's not dependent, it's independent. They come hand in hand. You have two choices for S. And by saying it's linearly independent, by saying this, I'm saying it's not that. If your teacher wants you to use the phrase linearly independent in your answer, you should say S is not a linearly independent set. Now, I want to show you that this stuff works. Remember I said that the zero vector is, the scalars equaling 0 always work? Well, if you let R and S both be 0, then that is, if you let C3 and C4 be 0, then so would C1 and C2. After all, 0 minus 0 is 0. 2 times 0 minus 0 is 0. If R is 0 and S is 0, we keep getting zeros. So that is the solution. And I'll tell you this, you made a mistake somewhere if your solution doesn't include the 0 vector. So what other vectors might work? Well, if I let S be 1 and I let R be negative 1. So this will tell me that C1 is negative 1 minus 1, negative 2, and C2 will be negative 2 minus 1, negative 3. Okay, what this is telling me is negative 2 times the first vector. To save space, I'll write it this way, please. Minus 3 times the second vector. 1, negative 2, 1. Minus 1 times the third vector. Plus 1 times the fourth vector. This is going to equal to the 0 vector. Let's try it. Okay, negative 2 minus 3 more is negative 5. Plus 3 is negative 2. Plus 2 more is 0. Let's do the last entry. That's 2 minus 3 plus 1 plus 0. Well, 2 plus 1 is 3. Take away 3 is 0. Add 0 and you get 0. And let me just make sure it works as a middle term. It works as a middle term too. This is negative 4 plus 6 is 2 minus 2 is 0 plus 0 is 0. So if you let the coefficients be like that, you'll have a linear combination that gives you 0. Now, we'll talk about this fairly nice theorem. I like this theorem as a student because I immediately saw that this set had to be dependent. If you have a set of vectors that includes the 0 vector, it must be a dependent set. If you have a set of vectors that includes the 0 vector, that set of vectors must be a dependent set. Let S equal V1, V2, up to Vn be any set of vectors which includes the 0 vector. One of those vectors is a 0 vector. Then S is a linearly dependent set. First, let's identify the 0 vector. Let V sub I equal the 0 vector. Okay. Now, so you have vector 1, vector 2, eventually vector V I minus 1, then vector VI, and then the vector after VI, and eventually Vn. The question is, can you come up with the coefficients? Can you come up with coefficients that are not all 0, but yet is it a 0 vector? The answer is yes. Let all these coefficients be 0. Let them all be 0, except the one in front of VI. Let's let it equal to 87. Well, think about it. This is a 0 vector. 0 times any vector. And we're talking about we're in a vector space. So 0 times any vector in a vector space is 0. 0 times any vector is 0. 0 times any vector is 0. 0 times this vector is 0. 0 times this vector is 0. These are all zeros, 0 vectors. They're all 0 vectors, including the ones in here. You have many 0 vectors, and when you add them all up, you get the 0 vector. Just a minor typo, nothing major. The bracket around the whole subscript. Okay, so far they added up to all zeros. But remember, that's the 0 vector. Oh, 87 times the 0 vector is also the 0 vector. You add up all those 0 vectors, you get the 0 vector. Now, somebody out there is like, I don't get this, and this stuff is hard. Where did he get 87 from? I just randomly chose this. I could have picked could have chosen any real number other than 0. Like it or not, I could have chosen pi. In a good mood, I didn't say e to the pi. But the bottom line is 0 vector plus the 0 vector plus a lot of 0 vectors plus the 0 vector plus another 0 vector plus a 0 vector plus more 0 vectors plus the 0 vector here equals a 0 vector. Okay? Okay, since not all scalars were 0, 87 does not equal 0. Since not all scalars were 0, we must conclude that S is a linearly dependent set of vectors. Let all the scalars be 0 except the one in front of the 0 vector. Pick any number but 0 for that one, and you'll be okay. It'll work like a charm. Even if you have abstract plus and minus, or plus and dot, excuse me. When you add the 0 vector, we proved it. When you add the 0 vector, you get the 0 vector. When you add the 0 vector, you get the 0 vector. Now here's a beautiful theorem. I saw this one as a student, but it was actually difficult for me to write up the proof. I remember that. Let S1 and S2 be finite set of vectors. Let S1 and S2 be finite sets of vectors with S1 being contained in S2. Every vector in S1 is also in S2. Then if S1 is a linearly dependent set, then S2 is also linearly dependent. B. If S2 is a linearly independent set, then S1 is linearly independent. Now, this makes a lot of sense. If S1 is linearly independent, well then how can S2 not be linearly dependent? If S1 is linearly dependent and everything in S1 is in S2, then S2 must also be linearly dependent. And if the bigger set, if this set is independent, how can S1 not be independent? Think why it's true. You have to think. None of this memorizing. There's a whole proof. Let S1 be V1, V2, up to Vk. And S sub 2, well, it contains V1. So we'll call it, due to lack of space, I'll write it in 2 rows. You have V1, V2, up to vk, and then you have the next vector. Call it vk plus 1, all the way up to v sub n. Okay? So let's do letter A. S1 is linearly dependent. What does that mean? That implies there exists C1, C2, up to CK, not all zeros, such that C1, V1 plus C2, V2, all the way up to CK, VK is the zero vector. Well, I know that whatever this is, whether it's a zero vector or not, if I add on the zero vector, it won't matter. C1, V1 plus C2, V2, all the way up to CK, VK. Now I'm going to add on the zero vector. So in the end, I'm going to get that same answer. And add on the zero vector. 0 times vk plus 1, that's the zero vector, plus 0 times vk plus 2, that's the zero vector, all the way down to 0 times vn, which is a zero vector. So we know from the line above, this is the zero vector, and I just added on the zero vector, just added, so I get the zero vector. But not all scalars are 0. Now, this is a linear combination of the vectors in S2. Not all linear. Okay, hence, S2 is also linearly dependent. They can add on zeros. So A is done. Nobody could say that A is not true. Now please, I want to take you back. I want you to say in class that A is not true if you don't understand the proof. You have to understand the proof. You know, maybe it's going to take you an hour or two to understand it, but at some point, the light bulb is going to go on. It's like, oh, he just added the zero vector. Why didn't he say that? Well, I did, but sometimes you don't hear the obvious. It always happens to me. Okay, now we can do the proof for B, but we're still going to let S1 and S2 be defined the way it is, the way I defined them. Okay, S2 is a linearly independent set. Okay. Suppose S1, so we want to show that S1 is linearly independent. Let's suppose it's not. Suppose S1 is linearly dependent. Now, if something goes wrong, that means this statement is false, which means S1 is linearly independent. Okay. So there exists C1, C2, up to CK, not all zeros, such that C1, V1 plus C2, V2, all the way up to CK, VK is the zero vector. Okay? Then C1, V1 plus C2, V2, all the way up to CK, VK, and then further on, namely CK plus 1, VK plus 1, all the way down to CN. Oops, making one little mistake, sorry. These coefficients are all going to be 0. For the last part, above VK, all my coefficients are 0. So I know that's a 0. I know that's 0 because we said it above. And I know that this is 0, So sure, the sum is 0. You add the 0 vectors, you get the 0 vectors. Now, commenting on this, then that equation equals 0 where not all scalars are 0. But that's a contradiction. That's a contradiction. Because if S2 is linearly independent, you can't come up with a linear combination of all the vectors in S2 that gives 0 and some of the coefficients are non-zero. This is contradiction since S2 is linearly dependent. The only place I could have made a mistake is here, when I suppose that S1 is linearly dependent. Therefore, S is linearly independent. It's one or the other, and if it isn't this one, if S1 is not LD, then it must be LI. There's no in between. Let's think about what we do next. Always more to be done. Okay. There. Let S equal the set of vectors V1 through Vn. Where none of those are 0. Let that set S be vectors in the vector space capital. Okay. So here's the claim. Claim. S is linearly dependent if and only if the following. It's a bit complicated to see initially. If one of the vectors Vj, one of the vectors in S, one of the vectors Vj is a linear combination of the preceding vectors. Which preceding vectors? Preceding Vj, V1, V2, all the way up to, I'll write it down here, Vj minus 1. Whenever S is linearly dependent, one of the vectors in that set, one of the vectors is a leading linear combination of the preceding vectors. Let's actually prove this. Thinking about now. So let's assume this. Assume S is linearly dependent. So what does that mean for us? Not all the scalars are 0. You have a linear combination of the vectors in S that equals 0, but not all the scalars are 0. So there exists C1 all the way to Cn, not all zeros, such that C1v1 plus C2v2 and so on all the way down to Cnvn gives you the zero vector. Now here's where it gets complicated. Now let Vj, sorry, just J actually. Let J be the largest subscript for which Vj is 0. Sorry, for which our Cj is not. Okay? We want the scalar. We want the scalar furthest along that's not 0. Okay? Some of the scalars are not 0. If it's C1, C22, and C23, or C213. If those are the only non-zero scalars, this is the one I'm concerned with. I'm concerned with the largest J so that the subscript is not 0. And now everything's going to come together for this half of the proof. Everything's going to come together rather nicely. Now, if J is equal to 1, then C1v1 is 0. And remember, Cj is not 0. So C1 is not 0. If J is 1, C1 is not 0. Which implies V1 is a 0 vector, which is a contradiction because I said no VI's are 0. Okay. Let's say so. So, J is bigger than 1. You know that. So, then now this one you have to think about for a moment or two. C1v1 plus C2v2 all the way up to CjVj is 0. I claim that sum is 0. Now remember, that's the largest coefficient. Cj is the largest term, largest scalar that isn't 0. That is Cj plus 1 times Vj plus 1, the next term. That's 0. So this whole product is 0. Plus Cj plus 2, Vj plus 2. That's 0. All the way down to Cnvn. That's 0. So 0 times the vector is 0. All the other terms in here, all the other terms that are beyond to the right of Cj, Vj, they're all 0. Now this is where it all comes together. You want to show that Vj is a linear combination of the preceding ones. But that's not a problem at all anymore. Cj is not 0. So solving for this, that is, bring all of these other terms to the other side. So Cj Vj is negative C1 V1 minus C2 V2 minus, including the term right before, Cj minus 1 Vj minus 1. Now divide by Cj. Divide by Cj. Divide by Cj, which is not 0. So Vj is this scalar times V1 minus this scalar times V2 minus this scalar times Vj minus 1. So yeah, one of the vectors, Vj, is a linear combination of the preceding ones. Here, I wrote Vj as a linear combination of the preceding ones. V1, V2, up to Vj minus 1. And that proof is, that half of the proof is 100% valid. Okay, now we have to show this the other way. Remember, we want to show that S is linearly independent if and only if one vector V sub j is a linear combination of the preceding vectors. We want to show that these two are equivalent. I've already showed that S is linearly dependent, implies one vector is a linear combination of the preceding vectors. Now we have to go the other way. Suppose, this is going to be the easy one. Suppose Vj is a linear combination of the preceding vectors. And everything comes together at this point. That is, V sub j is C1 V1 plus a scalar times V2 all the way up to a scalar times the vector before V sub j, which is V sub j minus 1. Scalar is called C sub j minus 1. Okay. Now, if I bring this to the other side, remember this is 1 times V sub j. If I bring it to the other side, I get C1 V1 plus C2 V2 all the way up to Cj minus 1 Vj minus 1 minus 1 times Vj. And this equals 0. If I bring this to the other side, then the left side is 0. Why is it on the right side? Because I switched the order. And I could say 0 equals that. Okay, but here goes. 0 is also equal to C1 V1 plus C2 V2 all the way up to plus Cj minus 1 Vj minus 1 minus 1 Vj. So far what I've written down is 0. Now I'm going to write down something else that's going to equal 0. And if this is 0, and what I'm adding is also the 0 vector, then yes, it will equal the 0 vector. Well, 0 times V sub j plus 1 is 0, and I go all the way up to 0 times V sub n is 0. So surely this is 0. But now, what happened was, is I have a linear combination of the vectors in S. V1, V2, all the way up to V sub n. And not all the coefficients are 0. And it equals 0. Since this linear combination equals 0, and some, call them scalars, some scalars are not 0, we now have we now have the set S is linearly dependent by definition of linearly dependent. If you can find the linear combination of the set of vectors or the vectors in a set that equals 0, some of the coefficients are not 0, that set is linearly dependent. Suppose you have a set S, and S prime is a proper subset of S. It doesn't equal to it. Is it possible that the span of S prime is equal to the span of S? Is this possible? Is this equality possible? That's what we're asking. Well, if S is equal to, say, V1, V2, V3, V4. S equals that is linearly dependent. Well, then, without loss of generality, say V4 is a linear combination of the others. One of them has to be a linear combination of the others. C1 V1 plus C2 V2 plus C3 V3. Okay? Now, the span of S is equal, the span of S is okay, vectors in the span of S. Let V be in the span of S. So V is a multiple of C1 plus C1 V1 plus a multiple of C2 V2 plus a multiple of C3 V3 plus a multiple of C4 V4. I was debating which subscripts I was going to change for the C's. How about we call these alpha, beta, gamma, and delta. Okay. Well, this is C1V1 plus C2V2 plus C3V3 plus C4 times V4. But V4 is C sub alpha V1 plus C sub beta V sub 2 plus C sub gamma V3. Okay, so let me fix that. I didn't need 4. V sub 2, C sub gamma, V sub 3. Sorry about that. Okay, now what's happening is I'm going to be able to combine some vectors like C4, C alpha V1 with C1 V alpha plus just distributing C4, C beta times V2 plus C4, C gamma, V3. So this gives me C1 plus C4, C alpha. times V1. So multiple of V1 plus C2 plus C4 C beta times V2 plus C3 times V3 plus C4 C gamma times V3. Okay, but this is in the span of S prime. This is a multiple, it's a linear combination of the vectors V1, V2, and V3. So this here is in the span of S prime. V is in the span of S, implies it's in the span of S prime. Of course, if you're in the span of S prime, I can show you that you're in the span of S. So right now, we have that. Right now, I have this. Right now, I have that. To show equal, I have to show it the other way. I have to show it the other way. So I don't forget, let V be in the span of S prime. We're just going to go the other way. Nothing going to be really different here. We just go the other way. A moment ago, we took away a vector. Now we're going to add a vector. We took away vector V4. We're now going to put in somehow the vector V4. Okay, so V is in S prime. Then V is a linear combination of V1, V2, and V3 plus C3, V3. But this is nothing more than C1, V1 plus C2, V2 plus C3, V3. You have to be clever. You want to introduce something, right? You want to introduce a new vector. So why don't you just add 0? Why don't you say take away? I don't even think I need a scalar. Let the scalar be 1. Take away V4 and add V4. Okay, so this is C1 V1 plus C2 V2 plus C3 V3 minus V4 plus V4. But that's how I'm going to write V4. That's how I'm going to write V4. C sub alpha V1 plus C sub beta V sub 2 plus C sub gamma V3. I probably should have just used the scalars B1, B2, and B3, but oh well. Okay, now I can combine these. Both of these are multiples of V1. So I have C1 plus C alpha times V1. I have a multiple of V1 plus I have a multiple of V2. C2 plus C beta V2. I have a multiple, I have two multiples of V3. So I have C3 plus C gamma V3. Minus, I'll put a scalar in, minus 1 V4. Okay, so V is in the span of S prime. But anything that looks like this, a multiple of V1 plus a multiple of V2 plus a multiple of V3 plus a multiple of V4 must be in the span of S. So once I show it both ways, I'm done. Therefore, the span of S is equal to, or the span of S prime is equal to the span of S. So it is possible to remove a vector from a set of vectors, so basically you have a set S, you delete one or more vectors, you have an S prime. The span of each of those could be the same. Must they be the same? Absolutely not. Because then you can do it forever. Well, not forever. You can keep doing it, and you'll always be left with only one vector. And, R2 is not spanned by one vector. Spanned by two vectors. But not just any two vectors. It can't be a multiple of one another. Okay. Now, let's move on to the theoretical exercises. We'll do a few of them. Suppose we have the following. Suppose S is equal to V1, V2, V3. The set S has those three vectors, and it is a linearly independent set of vectors in, in the vector space V. Now, given that, we want to show that T, which has the vectors W1, W2, W3, is a linearly independent set in V if W1, etc. are defined as follows. W1 is, say, V1 plus V2 plus V3. W2 is V1 plus V2. And W3 is just V1. Okay. So what we want to know, so here's our proof. We want to show, well, let's use C's instead. We want to show that a linear combination of vectors in W1, in T, let me write it down and say it. Here, if a linear combination of vectors in T, in set T, equals 0, the 0 vector, we want to know whether or not the C's are 0. The C1, C2, and C3 0. That's what we want to know. Okay. I took a linear combination of the vectors in T, and I set it equal to 0. I want to know if these coefficients, C1, C2, and C3, must be 0. Well, I don't know anything about about T, anything about W1, W2, W3, other than that it equals those vectors. V1 plus V2 plus V3. That's W1. Plus C2 times W2, which is V1 plus V2. Plus C3 times W3, which is just V1. Okay. And this still equals to the 0 vector. So what we have is C1 V1 plus C2 V1 plus C3 V1. And we have that number of V1s. How many V2s do we have? We have C1 plus C2 times V2. The only vector that's left is C1 times V3. C1 times V3. And this is 0. Okay? So we have a linear combination now of vectors 1, 2, and 3 that add up to 0. Oh, then these coefficients must be 0. I'm going to write the last one first. C1 must be 0. This must be 0. this must be 0. C1 plus C2 must be 0. But if C1 is 0, what do you add to 0 to get 0? 0. C2 must be 0. If this is 0, what do you add to get 0? 0 plus 0 is 0. And this is also 0. C1 plus C2, which is 0 plus 0, plus C3 must be 0. Well, if these two add up to 0, to get 0, the third one must be 0. C3 must be 0. Oh, wait a minute. You mean C1, C2, and C3 must be 0? Come back here. The scalars must be equal. So, T is a linearly independent set as well. I didn't do much here. I didn't do very much here at all. I used definitions and properties of linear and properties of vectors and definitions of linear combinations, linear independence, linear dependence. Okay, let's do the same problem again. S is equal to V1, V2, V3 is linearly independent. And T, once again, is W1, W2, vector W3. But this time the Wi's are defined differently. W1 is V1 plus V2. W sub 2 is V1 plus V3. And W sub 3 is V2 plus V3. The question is T linearly independent or linearly dependent? Oh, you want to know about T? Take a linear combination of their vectors. C1 and set it equal to 0. C1W1 plus C2W2 plus C3W3 is equal to the 0 vector. You need to conclude whether or not the coefficients must be 0. But I don't know anything about W's. I know about V's. Oh, how convenient. W1 is V1 plus V2 plus C2 times W2. But W2 is V1 plus V3 plus C3 times W3. But W3 is V2 plus V3. And this still equals 0. Now collect like terms. Let's do V1s first. I have C1 plus C2 V1s plus, how many V2s do I have? C1 plus C3. That is how many V2s I have. How many V3s do I have? C2 of them plus C3 of them. In all, C2 plus C3. Well, this last equation is a linear combination of just vectors in set S, V1, V2, V3. And set S is linearly independent. So these must be 0. These must be 0. C1 plus C2 must be 0. C1 plus C3 must be 0. C2 plus C3 must be 0. Let's see how we can solve this. This tells me that C2 is negative C1. Now let me say, okay, and this one I'm not going to change. C1 plus C3 is 0. But the next one is, I'm going to put negative C1 here. Negative C1 plus C3 is 0. Now, if I add these two equations, these two, if I add them, the C1s cancel out. I get C2C3 is 0, because 0 plus 0 is 0, and that means that C3 is 0. If I subtract these two equations, the C3s will cancel, and I get 2C1 is 0 minus 0, which is 0. Well, multiple of 2 gives you 0. The C1 must be 0. C1 must be 0. But C2 is negative C1. C2 is negative 0, which means C2 is 0. Since all the coefficients are 0, we go therefore T is a linearly independent set of vectors, because the coefficients had to be 0. There was no way around it. They had to be 0. I know. I worked it out. They were 0. No question about it. Okay. Do one more theoretical exercise. Okay. Let V1, V2, and V3 all be vectors in a vector space such that the set of vectors V1 and V2 is an linearly independent set. We have 3 vectors, and I'm telling you, 2 of them, V1 and V2, independent. Show that if V3 is not in the span of V1 and V2, that is, V3 is not a linear combination of V1 and V2, then the set V1 through V3 are a linearly independent set. Then V1, V2, and V3 are linearly independent. Okay. So now, what does it mean that V is not in here? Let's start the proof here. V3 is not in the span of V1 and V2. Is not in there. This implies there does not exist C1 and C2 such that C1, V1, let me say V3 first, such that V3 equals C1, V1 plus C2, V2. This is not possible. Not possible at all. Because if V3 didn't equal this, then V3 is a linear combination of V1 and V2, and that's exactly how you get to be in the span of V1 and V2. Okay. Now, we can do this proof by contradiction. Suppose, remember, so I want to find out where it is. We want to show that this set is linearly independent. So let's suppose the other way. Let's suppose V1, V2, V3 is a linearly dependent set. Okay. Then there is this C1, C2, C3 such that C1, V1 plus C2, V2 plus C3, V3 equals the zero vector, and not all CI's equal 0. Okay. If C3 equals 0, then just recopying this. If C3 is 0, then 0 times V3 is 0. So we just remove that 0 vector. We just get C1 V1 plus C2 V2 is equal to the 0 vector. Okay. But we can make a comment on this one, because V1 and V2 are linearly independent. They said that. Where are we? V1 and V2 is linearly independent. So if this linear combination of V1 and V2 gives you the 0 vector, then C1 equals C2 equals 0. But then C1 equals C2 equals C3 is 0. Because right now we're talking about all the coefficients being 0. But I just want to find out where I said it. I said there exists C1, C2, and C3 such that that linear combination equals 0. And not all of the CI's equals 0. So we have a contradiction there. Okay, that means C3 can't be 0. So C3 is not 0. Okay, so C3 is not 0. Then C1 V1 plus C2 V2 plus C3 V3 equals 0 gives us, I'm going to solve for V3. C3 V3 is negative C1 V1 minus C2 V2. That's what C3 V3 is. But I'm going to divide by the non-zero number. So I wrote V3 as a linear combination of the other vectors. But this implies that V3 is in the span of those two vectors, is in the span of V1 and V2. But that's a contradiction. That's where the proof comes together. We just said that it's not in there. So let me think a minute. So the set V1, V2, V3 is not linearly dependent. is not linear independent. That is V1 to V3 is linearly independent. That is V1, V2, V3 is linearly independent. The set V1, V2, V3 is certainly linearly independent. And this completes the section on linear independence.